the rotating and the static. Static is the transformer. Static in the transformer, we have learned it in chapter 2. Chapter 2. Transformer. But for the rotating, we have learned the DC machines in chapter 7, and the induction machines in chapter 6, and the last one, synchronous machines in this chapter. There are also some other kinds of machines. For example, step motor, line motor. They are not in this textbook.
But the distribution motor is DC.
You can learn it by yourself. The other kind of machines, there are many kinds of machines. So today we'll introduce the synchronous machine. Synchronous machine is the most important type of electrical machine. Most important. It mainly used as a generator. It runs at a constant speed. The speed is proportional to the frequency of the power, and it's proportional to the number of the poles. There may be 2 poles, maybe 4 poles, many other poles, other number. Although it's usually a generator, but sometimes it can be used as a motor. Sometimes it has not used, but most times it runs as a generator. Just because it runs at a constant speed. It is manufactured to generate electricity in power plant. Generally, there are 3 phases. Synchronous generator. So here we call it synchronous generator. As the primary source of electrical energy, we consume today. They are widely used in industrials and others. Rubber mills for air compressor, and pump, and other applications. We know 99% of the power is generated used synchronous generators. It can be oil, nuclear, hydroelectric, and the most is coal. It will induce the air pollution. So in China, the percent is about 50% of the electricity is by the cool. So our air is we can't see the sun so clearly every time. Okay. Yeah. So the primary electricity source it can introduce it can generate electricity. So it moved by a prime mover. In the progress of the energy conversion, there are also some losses. For example, the iron losses, magnetic losses, and the copper losses, just as we have studied in chapter 6 and chapter 7. The input is prime mover, maybe the coal, maybe the gas, maybe the oil, to drive it to rotate. The output is the electricity, three phase, 50 Hertz or 60 Hertz. Most of the electrical power is obtained by the coal data. And we see here the generator here, the G designated by the G. The G is the synchronous machine. So it's used as a generator. So this is just a simple graph. So the principle of the power plant is simple. It's easy to understand. So this heat and the hot water and the cold. So it's the cool water. Okay, let's see a big one. This is a hydroelectric set. So the volume is very big and heavy. In China, there is a big power plant about hydroelectric. Because the name is Sanxia. So this is the introduction. And we'll introduce the construction. Just as the DC generator, the synchronous machines have also the stator and the rotor, and also there are the slip ring. Slip ring is also how in induction motor, the wound rotor type of induction motor also have the slip ring, but it has three rings because it's three phase. But here just two because the current is direct in the rotor, direct current. So just two rings. This is a stator. It's the same. It's the same as the induction machine. It's the same. it has three phases and have the slots, many slots. So here this example is 36 slot, maybe other numbers, and hundreds of slots. It's a cylindrical portion inside the machine. It has three phase distributed windings in the slots. The stack frame is manufactured by the iron, and the stack is laminated material. The coils placed in the slot, maybe single or two layers. The right is two layers. The left is a single layer. So this is just the same as the DC motor and the induction motor. So we can see the coil. This is a single layer. In each slot, have only one coil, one winding. But in this one, it's double layer. So in each slot, we have two coils in each slot. So generally, two is okay. So in most applications, they use the two layers for better performance. And we see this graph. This is people here. So this data is very large. That is very large. Because the power of the generator is large. It's mainly used in hydroelectric power plant. But in coal plant, it will be a little small. After the stator, we'll see the rotor. The rotor, there's a little difference. The rotor, also we know it's the rotating part of the machine. This is the model. It produces magnetic flux. When it excited by DC voltage. So DC voltage is added by the ring here. DC windings are placed in the rotor slots. So rotor experience very magnetic fields. Therefore, is constructed of thin laminations to reduce the eddy cut losses. To supply the rotor winding while it is rotating, some special arrangement will be employed to connect it. We see not this one. So the supply of the DC rotor the rotor is DC DC power. So this is different with the AC induction machine. If for a squirrel cage induction machine, there's no sources to the rotor, and in wound rotor induction machine, it can be give a three-phase alternating current to the rotor, but here we just give the DC current to the rotor. Let's see the two types of rotor. The left one is a cylindrical rotor. So it's in the rotor cylindrical, but the right one is a cylindrical rotor. So this is the four poles rotor. This is two poles. It's the air gap. So in this one is air gap between the stator and the rotor. So it's constant. The air gap is constant. But in the cylindrical rotor, the air gap is not constant. So here is narrow, here is wide, so it's not constant. And also the two graphs is the same. So we also call this one is uniform air gap. We see here the ring, two rings. So the rings are the same. It is supplied by the DC surface. And we'll see it in detail in this picture. This is the cylindrical rotor. So this copper wire. So this windings. So also the cylindrical rotor, also we call round rotor. It are manufactured in small number of holes and high speed, high revolution per minute, high speed. So this the cylindrical rotor usually used in high velocity steam turbines. The length of the rotor is long, and the radius of the rotor is small. In this type of cylindrical rotor. You see here the speed maybe this is the four poles, and this two poles. So the speed is high. Usually used in the steam. So this type of rotor is used in these applications. See a picture. It's just like this. So it's very long, and but the diameter is small. So it's a cylindrical rotor, and these windings. We see the windings in the slots. The winding is the field windings. Many windings in the slots. this is a clear. This is a clear picture. Okay, let's see. This is one. The number is 18. 18. 1 to 60. And also we see another kind of rotor, standing pole. So the picture is this one, which was not very clear. So we see this part is the pole. This part is the pole, and the top of it we call it the pole head. And the windings and this winding. We see this picture. We can see that the length of it is not very long. It's short compared to this one. The length is a little short. But the radius long. So this kind of sending rotor are used in hydroelectric power plant. So applications of the two type of rotors are different. We see the differences. First, the speed. Speed is so slow, about 50 or 300 RPM. But we know from the previous sliders, the cylindrical rotor, this speed is about 3,600, maybe 1,800. But here, for the standing pole, the speed is too low. Because it's mainly used in the hydroelectric power. We know the speed of the water is slow, so the speed of the generator for hydroelectric is slow. There will a large number of poles. We know the speed is inversely proportional to the number of the poles. So this kind of rotor can have a large number of poles, maybe 50 or 60. And also we know the air gap. And that is not a constant value between the rotor and the stator. We see two pictures. The Chinese characteristic. So it's a hydroelectric power plant. So we call this the hydro generator. This one. So this is the picture, and then we'll see another pictures. So the power of this one is so big. It's a large, power, high power. But this is for hydro generation. And we see this picture is one pole of the rotor. It's just a pole. There are windings with is the head. It's also laminated. laminated. We just have a comparison of the two types of the rotors. So we should remember these conclusions. The air temp is different. The diameter for this one high, but for the cylindrical one it's small. But the length for the cylindrical, the length is large. But in cylinder, the length is small. We just have see a lot of the pictures of the two types of generators. Okay, let's see the other parts. We know the stator and the rotor, but also how slip rings. You see the two slip rings out here. It ended the DC sources connected here to generate the magnetic flux. This is the brush. So it's different with the DC motors commutator. And we'll see one end of the rotor windings is connected to the ring. Windings is connected to the rings. And we see here there's some problems. With springs and brush, just as the DC motor it will require the maintenance. It will influence it will lifetime. It shorten the lifetime. And also their voltage drop on the brushes, so there will be power losses. But in some, okay, we'll see the next. In some smaller power applications, we will use this. We use the rings and brushes because it's cost effective. But in high power generators, we will have the brushes. But how to realize brushes? We have some other methods. Let's see. So this is the brushless exciter. So this is important. Usually used in high power. We see it here. From here, this is the synchronous generator. This is the stator stator windings, three-phase stator windings connected to the AC sources to the grid, connected to the grid. This is DC field winding. In small power, we just use rings and brushes, here to connect to the DC power. But in high power, we use this method of brushless exciter, pushing this part. This part is also rotating with the rotor. So this part is rotating.
Sir, this is three phase. Sir, is it three phase? Three phase?
Three phase?
This is three phase.
Here,
Three phase.
three phase.
Yeah.
Here the DC is 2, but
this
the
motor.
DC is rectified by 3 phase. So here is the
Three phase.
generator.
Yeah.
It's a 3-phase AC generator. So it's AC generator to generate 3-phase AC current, AC voltage, and the AC current is converted to DC, by this part. This part we call the rectifier. So because this part is rotating with the rotor, so there will not need the rings. You cannot need the rings and the brushes. So it was brushless. But we see here, this AC generator, it also needs exciter how to generate the field flux for this one. We have another windings. This is the exciter stator. So this is stationary. This is stationary. So just here is AC. This is the stator. This rotor. AC generator. To generate AC current converted into DC to the synchronous machine. So this is a complete complicated system. The voltage here is high. Voltage here is high, but the voltage here is low because the power is low power. But here the power is high. So we see the schematic. This is the schematic graph. I just see from the right. Here is synchronous generator. So the down part here, this part is the stator. This stator, and the up part is the rotor. We can see here. This is a DC field windings. DC is come from the small AC generator small AC generator, it has its own stator. The stator is here. It can also power the bar. So the DC current, for this AC generator is come from another three-phase source. So there are three sources. So this source power this generator to generate the current, power this part, to generate the flux. Use this complicated method, we realize the brushless. So everyone can understand the principle of the brushless exciter. So maybe it's a little hard. I will find if there's a video in it. It will explain more clear. Okay, just take a break. I will find the
electromagnetic induction. To generate electricity in a coil, either the coil should rotate with respect to magnetic field, or a magnetic field should rotate with respect to the coil. In the case of alternator, the latter approach is used. Rotor and armature coils are the two main parts of an alternator. Rotor produces a rotating magnetic flux. Armature coils are stationary. And rotating magnetic flux associated with the rotor induces electricity in the armature coil. This kind of rotor shown here is known as salient pole rotor. For gaining better insight of its working, let's consider a rotor with just 4 poles. Rotor coils are excited with a DC power source. Magnetic field produced around it would be as shown. The rotor is made to rotate by a prime mover. This makes the rotor flux also rotate along with it at the same speed. Such revolving magnetic flux now intersects armature coil, which is fitted around the rotor. This will generate an alternating EMF across the winding. Here is a slowed-down version of rotor-stator interaction. For this 4-pole system, when the rotor turns half revolution, induced EMF takes 1 complete cycle. It can be easily established that frequency of induced EMF, rotor speed, and number of poles are connected through following relationship. It is clear that frequency of electricity produced is synchronized with mechanical rotational speed. For producing 3-phase AC current, 2 more such armature coils, which are in 120-degree phase difference with the first, is put in the stator winding. Generally, one end of these 3 coils are star connected, and 3-phase electricity is drawn from the other ends. It is clear from this equation that in order to produce 60 Hz electricity, a 4-pole rotor should run at following RPM. Such huge RPM will induce a tremendous centrifugal force on poles of the rotor, and it may fail mechanically over time. So salient pole rotors are generally having 10 to 20 poles, which demands lower RPM. Or salient pole rotors are used when the prime mover rotates at relatively lower RPM. Pole core is used to effectively transfer magnetic flux, and they are made with fairly thick steel lamina. Such insulated lamina reduces energy loss due to eddy current formation. Armature winding of three-phase 12-pole system is shown here. A stator core is used to enhance magnetic flux transfer. DC current is supplied to rotor via a pair of slip rings. DC current is supplied either from an external source or from a small DC generator which is fitted on the same prime mover. Such alternators are called self-excited. With variation of load, generator terminal output voltage will vary. It is designed to keep the terminal voltage in a specified limit. An automatic voltage regulator helps in achieving this. Voltage regulation can be easily achieved by controlling the field current. If terminal voltage is below the desired limit, AVR increases the field current, thus the field strength. This will result in an increase in terminal voltage. If terminal voltage is high, the reverse is done. Hope you have a nice introduction to working of alternators. Thank you. Voltage will vary. It is designed to keep the terminal voltage.
So we see here the DC power is from this DC generator. So there are two brushes and the commutator and the brushes. So there are so many brushes, like 4 brushes here. So there are brushes. There will be losses here. Will influence the lifetime. So in high power generator, we use brushless. So next video we'll see the brushless method. Yeah, this one I will show you the next week. But today you see the motor. But we know just see the generator and see the brushless. This tool is next week. Just similar. We see this one.
This is brushless excitation system which provides the field current to the synchronous generator without using slip-ring carbon brushes. As compound resistance losses will be eliminated, brushless exciter system is coupled with rotor shaft hereof. The parts of exciter 16-pole permanent magnet exciter PMG which produce 400 Hz, 220 VAC supply and 3-phase.
So this is not a good one, but we make this one good.
DC current from the rectifier is supplied to the rotor winding from the collector rings on the shaft. The rectifier is supplied from a dedicated transformer. The primary side of the transformer is fed from an auxiliary bus, or in some cases, the generator bus itself. The sine wave for the incoming three-phase DC voltage, which which is applied to the rectifier, will look like this. After rectification, the DC output can be represented by this curve, and this may be further smoothed to look like this. The level of DC voltage can be adjusted by controlling the firing of a thyristor type rectifier. The firing circuit is controlled by the field voltage regulator. This regulator has two inputs, manual and auto. The manual control disconnects the automatic function and allows the operator to directly control excitation. However, when the generator is in operation, the field voltage regulator is usually controlled from the auto position, that is, from the AC voltage controller. This controller monitors the generator bus output voltage through PTs and automatically adjusts excitation to maintain the set point voltage. The operator can adjust this set point and thus exercise control while the excitation system is operating in auto. All of these components of the static excitation system are normally located in the excitation panel close to the generator. Of course, the auto and manual control inputs are also located on the operator's panel. Another type of excitation system often used is known as the brushless exciter. The exciter is actually a small AC generator which is built on the end of the generator shaft instead of collector rings. In this exciter, a stationary magnetic field is provided from the DC winding, which is wound on the stator. The rotor winding produces AC voltage, and this is fed directly to the diode type rectifiers, which are built into the shaft. So we have, in effect, a rotating rectifier. The DC output from the rectifier is connected directly to the main rotor winding through leads which pass inside the shaft. There is no need for collector rings or brushes. Control of the DC excitation current is affected by adjusting the strength of the exciter magnetic field, and this is done by controlling the DC current flow through the field winding. This DC field current is supplied from a rectifier which is located in a nearby cabinet. Of course, this rectifier is much smaller than the static rectifier that we previously studied because it is only supplying field current to the rotating exciter. However, control is effected in the same manner, that is, by adjusting the firing of the thyristors, and this in turn is governed by the field voltage regulator. The arrangement at this point is similar to the static exciter. When in auto, the field voltage regulator receives its command signal from the AC voltage controller, which in turn monitors the output voltage of the generator. The operator can adjust the AC set point as required. When starting up the unit, the field voltage regulator may be set to manual, and in this case, the operator will control the regulator directly.
So you can see here, the larger generator need a small generator to generate the power, the field power. A larger generator need a small generator. Okay, this is the principle. The next one, you can see it by yourself. And then we will see also the PPT. The video help us to understand the principle of the brushless exciter. So here we will not explain any help. Here this all the we'll introduce the ratings of the synchronous generator or synchronous motor. The ratings are easy. Just the power, the voltage, the current, the power factor, frequency, speed, of field voltage. Just these items. We first see the voltage, speed, and frequency. We know the frequency maybe 50 or 60. In some special applications for the aircraft is 400 hertz. 400 hertz. These are the three kinds of frequencies. And if we know the frequencies, and we can calculate the synchronous speed, just as we calculated in induction machines. So the speed can be calculated. If we know the speed of the rotor, and also we can calculate the frequency. So these two equations are easy to understand. And we know that the armature voltage proportional to the speed.
Speed and this flux.
So if we can use the 50 hertz 60 hertz generator operates at 50 hertz. If in low power, so it's no problem. But if in industry applications, the voltages should be changed to 80%, 83%. Just use this equation. So if the frequency changes, the field voltage would also be changed. And also we see the voltage. We can here the voltage depends on the flux, the speed, and the mechanical construction. And also the speed, the voltage is limited by the insulation limit. And then we'll see the power and power factor. Also the apparent power. So this equation to calculate apparent power. And this is the line. Line voltage. Also calculated. And we'll see the power factor. The power factor of the armature current is irrelevant for heating and armature windings. So it's so we see the red character. It's possible to operate the generator at a low power factor. It's a landing power factor, so it's no problem. We just should understand it's okay. And we'll see the short time operation, short time operation. We know a machine can work three times of the rated power. Three times the rated power. We see the instance. It can be supplied 1.5 times the power of it, but the time is short, only for 1 minute. If it takes too long, it will break down. It will destroy the generator just for a short time. Less than 1 minute, 1.5 times of the rated power. And we see the service fan. Generally, the service fan is 1.15, just 15% up to the rated power. So this is some ratings of the synchronous machines, and the operation mode we'll take next. Tomorrow. Okay, today